Hello, so in today's session, we're going to talk about trigonometric functions. So, in this chapter, we're going to start with going into periodic behavior. So, periodic behavior or periodic function is generally the kind of function that repeats itself over horizontally. Examples of these functions would be something like the wave function, where at some point, like from one cycle, it would repeat itself again. It would repeat itself over a certain period of time. And well, it doesn't necessarily have to be a wave function. It can actually also be a function that looks something like this. So this function is what happens when you, for example, try to roll a circle, which goes like this, and we want to track one of the points in the circle, and it would form something like this. And this would, this is what you call as a cycloid, and this is also a form of periodic function. And okay, so usually in periodic functions, we're going to go more into waves. So we're gonna talk about that. Okay. So a wave in general would always oscillates in the principal axis. So what the principal axis is essentially its middle line, or the middle ground, which divides the period and makes it look like it's actually a moving periodic thing. It's like the middle ground between the minimum and the maximum moment. So this is period, and this is the minimum point, or known as the trough. And this is the maximum point, or known as the crest. And then there's also something called amplitude. The amplitude, you can say, is kind of similar to the height of the shape of the crest or the trough. So it's the distance between the principal axis to the maximum point, or the distance from the principal axis to the minimum point. And last but not least, we have period, which is basically the like the space which the function repeats over time. Like this would be something the function would continuously repeat, and this is what you call as one period. It's kind of like the pattern, the shape of the pattern that would be repeated. That is a period. Okay, so when we're drawing or talking about waves, we can go into the sine and cosine function. Okay, so as we learned before in the unit circle, where this is 1 minus 1, and this is the origin, we learned that the point x here, the point, let's just say point A here, is equals to cos theta over sin theta. So if we graph sin theta and cos theta, it will show you that sin theta is in the form of something like this. Well, cos theta would be something like this. Actually, let me clear this up so you can like have a direct comparison of it. Okay, so this is sin, and then this is cos. Oops. So in this graph, the maximum points of these would be 1, and the minimum points of these would be -1. And basically what's going on is that when sin theta is like in a certain point, there's some ratios that you can get from the values of the graph, and same goes for cos. So from 0, this is 1, this is, let's just say this is pi over 6, and then pi over 3, something like that. This is going to be square root of 3 over 2, and then another one is going to be 1 over 2. And this is also pretty much same in the unit of circle. 1, 1. If we have if we have something like this, and let's just say this is sin cos pi. This is cos theta and sin theta. That would be pi over 3 over 1 over 2, and then 1 over 2, comma, square root of 3 over 2 minus, no, square root of 3 over 2, and etc., etc. Okay. So, for example, this is square root of 3 over 2, comma, wait, this is, oh, my bad, this is 1 over 2, comma, minus square root of 3 over 2, and then this is square root of 3 over 2, comma, minus 1 over 2, and etc., etc. So this, how do you say, this quadrant or this unit of circle reflects the forms of these sine and cosine functions. Right, so after that, we have the properties of the sine and cosine functions, which is that right, this is cosine, this is sine. So they have similar properties since they look like the same. They look like the same wave. However, one is just shifted back or shifted front. So like I said before, they have the same amplitude, which is 1, and then they have the period of 2 pi. This is pi. This is, yeah. So this is 0. This is pi. This is 2 pi. And same goes with this. So even though the shape wait, my bad. This is, oh yeah, my bad. My bad. This is pi, and then this is 2 pi, and then this is 3 pi. So as you can see, even though the shape is different, the pattern of it compromises of 2 pi. Because after like the 2 pi, the pattern starts repeating again. And then the principal axis would be y equals 0, because to find the principal axis, you need to do maximum point plus minimum point of the y over 2. and that gives you 1 plus 1 over 2, which is, well, 2 over 2 or 0. Okay, so since you can obviously see from the graph that one of them is shifted, then we can say that sin theta is equals to cos theta minus pi over 2. Because if you're, let's just say we have sin, and then we have minus pi over 2, which is kind of like saying, as we learned before, we've learned about the shiftings of the graph, right? And if we have x, like fx minus b, oh wait, fx minus a, that's equals to the a having horizontal shift. So what's going on in here is this graph with minus pi over 2, it would be shifted so it becomes something like this, which resembles the graph of cos that we have. I'll just redraw this in another color so it's more clear. There. So this is the wait. Okay, so it's like this. Yeah, this is the other estimate of the cos graph. And then if how about cos theta? So cos theta would be sin theta plus pi over 2. Hold on, I forgot to turn off the waiting rooms. Okay, so when drawn in as a shift, it would look like you're moving it to the side, which makes it look like something like this. So from that we can okay, so after that we can establish like the sinusoidal model, which is y equals to a sine b x minus c plus d. So I'm gonna clear this for a sec. Okay. Y equals to a sine b x minus c plus d. And it also applies the same for cos in this context because of how similar the properties the graph looks, except for the shifting, that is. Okay, so basically what's going on right here is that the a functions as the amplitude of the graph. So if we have a graph like this, okay, to make it easier, let's just demonstrate things in the sine graph first. Because the cos graph works similarly, just, you know, it's shifted, that's all. So if you multiply it by a, then it would stretch vertically by a. That's why a is basically the amplitude. Maybe if I have different colors, they will look nicer. Okay, there you go. So we have A, amplitude, something like this. So this becomes the A. And then if we have the D, the D would be the shifting of the graph. So originally it's like this, but then if you shift the shift it, it would by D it would have a vertical shift. So it becomes something like this. So like the overall graph itself gets moved vertically. And then for B, let's just do B first. For BX, that would be the horizontal stretch. And it would either squeeze the graph or expand the graph, so it becomes more, it becomes wider. Then lastly, we have C, which is the horizontal shift. And it basically from this graph, it can move into, like I said before, it shifts horizontally, so you can pretty much turn the sine graphs into cos graphs using these. So, okay, I think this is done for now. Okay, next up we have modeling these functions, which is basically what you do to model these functions is that you need to know like the amplitude of it, the horizontal shifts, the horizontal stretches, the vertical shifts to be able to model them. Oh yeah, let me just write down vertical shift. This is D. Oh, and also one more thing to keep in mind is that if you have a sine graph or sinusoidal graph, and you have a period, the period would be 2 pi over b. So the reason why it's 2 pi over b is because the standard sine graph, the standard sine wave or the sine function or the cos is in form of 2 pi. But then if you have b as a horizontal stretch, that's like multiplying the formula by a scale factor of 1 over b. So to find this, basically you just multiply the period of the sine graph by its stretch factor, which is 1 over b. And that's how you find 2 pi over b. Okay. I think this is for AA, and basically in AA, there are times when the question asks you to estimate the trig models. I personally find this more in like for stats, but I don't know why it's an A. So basically, if like in the question you're going to have a list of statistical values, And the values, if you plot it in your GDC, it would look like something like, well, it would dot around some sort of trig graph. And by inserting it in your GDC, you can calculate the sine regression or the cost regression of the graph and find like an estimate shape of it. So yeah, that's pretty much it. You just need to learn to figure out how to do it. And I'm not the best teacher to do that because again, you have different calculators for GDCs, so it's better to just Google it. And then next up, we have the tangent function. So again, this is also kind of derived from the oh, sorry. Your mic is kind of choppy. Okay, so since the mic is kind of choppy, I'm gonna continue. You can always put it in the chat. I'll keep it open so I can read it. Next up, we have the tangent function. So basically, in the unit circle chapter, we talked about how, like, if we extend it, you would get this length of the coordinate as 1 and 10 pi, and how that that also gives you 10 pi, and okay, also this point would be cos theta, sin theta, and how this gives you 10 pi over equals to sin theta over cos theta. And we also know that in the tangent function, in the properties of tangent, it would be positive in the first quadrant and the third quadrant. Well, it would be negative in the second and fourth. And okay, something else to know about is that the period of the tan function is it would be in terms of pi. Because this is basically how the shape of the graph looks like. Pi over 2. Okay, so if you insert the values of the tangent, is essentially sin over cos, like literally sin over cos. So if you have 0, what else, pi over 3, etc., you just do sin theta value over cos value. You don't need to like remember it very well. That would help you find the answer. And if you graph it, this would be the result. And you can see that the form of it would be this and this, and then afterwards it would just repeat and again from here and here. So the tan function also have its own properties because of this difference. Oh my bad, this is actually bx minus c plus d. I'll fix that later. Bx minus c plus d. So like before, the d is used the d is used as its principal axis, or it's like its horizontal shift. No, sorry, it's vertical shift. So if you have a change in d, like plus d, then it would look like this, something like this-ish. So it will shift up or down depending on the value. I mean, if d is negative, then it would shift down. If d is positive, it would shift up. And then the period is I over b, since you know it's the period, the initial period times the scale factor of it. And then uniquely in this graph, you don't have an amplitude. Even if you do, the amplitude of it is undefined, because there are certain points in the graph where the function is undefined, such as when you have pi over 2. So that's why you don't really have an amplitude. And the basically it has infinite vertical asymptotes if there's no limit to the graph. So you can have as much asymptotes as you want, as long as you don't put restrictions or limitations to how much the graph you want to include in the question. Okay, so since you see that like the graphs we had before, the sine graph, the cos graph, the tan graph, they all repeat and repeat, it will have infinite solutions. You will have a non-ending supply of solutions, unless if the question asks you to restrict the solution that you're going to have. For example, the most common restriction that you'll get is usually 0 is bigger or equal to x, which is bigger or equal to pi over pi, or 2 pi, or 2 pi. So usually this is like one of the more common restrictions which they will have. And if this is the case, that means that, like, let's just say this is the restriction. So you will only have this portion of the graph. Wait, actually, my bad. This portion of the graph. So let's just say you have to find the value of a, and the value of a is here. So that means you're going to have 2 solutions for this, and you're going to have to find all the solutions for it, both this and this. Okay, so there are several ways to solve the trigonometric function. The first one is using the graph, like what I did before. So basically, you try to estimate the points where they have the solution in. And then the next way to find it is using your GDC. So in your GDC, you can always graph the function that you have. And after graphing it, you can look for the points that they have and get your solution. And last up, you have the using your algebra solution. So there are times when the you can find the solution using algebra. So basically, how you do it, let's just say if you have a sin x x minus c plus d, and you're trying to find the solution when it's in 0, then how you find it, it would be that you try to algebraically move it so that you can find the value of x, and you calculate it from there. But you mustn't forget that you're going to have several solutions most of the time. So you have to apply the formulas or the techniques to find the other positive values. For example, in sin, you have sin theta equals to sin p minus theta, and etc., depending on your value. Okay, and then last, we have using trigonometric models. So basically for this, you gotta do lots of practice, man. Yeah, you literally just need to do lots of practice so you can ace this part. And that's it for today's session. Thank you for coming.